Hey guys, today we're going to be talking about the limit existence theorem. And this limit existence theorem tells us that a limit as x approaches a of f of x exists if and only if the limit it approaches from the left side is equal to the limit as it approaches to the right side, which is equal to b, and b has to be some real number. So let me write all that down so you can see it. That way you can come back to it and be able to use it later in some of the problems or examples that we're going to do. So the limit existence theorem tells us the limit as x approaches a of f of x exists if and only if the left-hand limit, or the limit as x approaches a from the left-hand side, f of x, is equal to the limit as x approaches a from the right-hand side of f of x, which is equal to b, where b is any real number. Okay, so here's the big thing about this that a lot of times kids get confused with, is talking about where b is approaching a real number. We'll have times where a left-hand limit may be approaching infinity or negative infinity, and we just have to remember that infinity is not a real number. Therefore, if we have a limit that has a left-hand or right-hand limit that is approaching infinity, we can stop right there and state that the limit does not exist. So what I'm going to do is I'm going to draw a few things here and go through a few times where a limit doesn't exist and where a limit does exist. So here we've got our coordinates plane drawn here. Let me go ahead and mark a vertical asymptote somewhere through here, just so we can have that example. So let's say there's a vertical asymptote there. Now I'm going to draw, just bear with me, I'm going to draw some type of graph over here on the left hand side. So we have our graph here, and then on the right hand side, let's draw something else. Let's just have the exact same thing on the right side, and we've got arrows on both ends because it is a continuous function on both ends. Okay, so now let's talk about limits at different approaches. At first, let's just go ahead and say that this vertical asymptote is occurring at x equals 2. So now if I was to ask you a question here and I said the limit as x approaches 2, and I ask you what is that equal? Well, the first thing using our limit existence theorem is we're going to have to see what is the left-hand limit approaching, or what is our value approaching, or what is our y value approaching as x approaches 2 from the left-hand side. So let's go ahead and see what our left-hand limit is actually equal to. So 2 from the left-hand side of this f of x function is equal to, well, if I look here, I can see that as we get closer and closer and closer to this 2 value, we're actually, our y value is actually approaching infinity. So by our limit existence theorem, is it possible at this point for this limit to exist? And the answer is no. But just for purposes of checking our right-hand limit, just so we can have some practice approaching that, let's go ahead and do as x approaches 2 from the right-hand side of this f of x function. And let's see, we can tell that as we approach it from the right-hand side here, that it is also approaching positive infinity. So a lot of times what people mess up on this is they see that the limit is actually approaching the same thing, so they want to answer it in this way. They want to answer this to equal infinity. But if we look at our limit existence theorem, it tells us that it has to equal a b value where b is a real number, and infinity is not a real number. Therefore, that would be the incorrect answer, and the answer should be undefined, or we can write it as does not exist. So there's an example of the graph where we can see that the limit does not exist. Now let's pick some other value here. Let's go here and we'll say that's x equals, let's say 4. Okay, so if that's at x equals 4, and now all of a sudden I'm asking for the limit as x approaches 4, and I want to know what its solution is of f of x. So we go through our process here graphically to see what is this value approaching. So I guess I need to go ahead and give some y value here. Let's say that that y value there is 1. Okay, so that y value there is not -1, just +1. Okay, so that's equal to 1. So now when I evaluate my limit here, we go for our left-hand limit. The limit as x approaches 4 from the left-hand side of f of x is just equal to, looks to be 1, because as we get closer and closer to that value from the left-hand side, it's getting closer to that value right there, which is a y value of 1. Now we're going to do the same thing, but now with a right-hand approach. So the limit as x approaches 4 from the positive side of this f of x function is going to equal 1 as well, because we can see here that as we approach from the right-hand side that we end up with 1 as well. So now, since these two values here are equal, since my left hand and my right hand limit are equal to each other, and the value that they're equal to is a real number, then the limit as x approaches 4 of f of x would just equal 1. Okay? So that is a way that we can look at our function here graphically. So now, what if I give you some function and we have to evaluate this function analytically? So we're given a function. Let's see if I can find one here that I can use. I'm not really good working or making these up. So let's just see what we would do if we just had a function. Okay, so analytically it's a little bit different. So if I use this value or this limit as x approaches, let's say 3. So as x approaches 3 of, let's say, x squared minus 2x plus 3. Okay, so analytically it's a little bit different here, because graphically we were given a graph. We could see what its output values are. We could see at any point where there was a vertical asymptote, or if there was any type of discontinuity in our graph, we could see that graphically. But now analytically we're going to have to be able to recognize whether it's a vertical asymptote, whether it's a removable discontinuity, or if it's just a continuous function. So if we look here at this first one, it is a continuous function. We can see that this is a quadratic, so it's going to be continuous for all x values, because our domain would be from -infinity to infinity. And at any point that we have a continuous function and we're evaluating a limit, we can just take this x equals 3 and plug it in, because we can see that the limit of this function would just be equal to 3 squared minus 2 times 3 plus 3, because when I evaluate that, that's going to tell me the y value at x equals 3. So we can see that the function from the left side and the right side of this, since it's continuous, will be approaching whatever y value that might be. And in this case, it would equal 9 minus 6 plus 3, which would just be 9 minus 6, which is 3, 3 plus 3, which is 6. Okay, so there's a look at it analytically when we have a function that has no problems with our domain. But now let's see if I can come up with something that may cause a problem in terms of our domain. See if I can think of one here. Okay, let's just use something that's got a difference quotient in it. That makes it a little bit easier to work with. So now the limit as x approaches 1, let's just put x minus 1 on top, and then we're going to use the difference quotient on the bottom. So now the big problem here becomes that when I evaluate this limit, it's going to cause a 0 on the bottom. Okay, so that 0 on the bottom is telling me that there's going to be some type of discontinuity, whether it's a removable discontinuity or if it's going to be a vertical asymptote. And the way that we can tell that is if we're going to make each part of this be linear factors, or we're going to rewrite it as linear factors. So I can see the top, or the numerator, is already in a linear factor, but now I need to make the bottom as a linear factor, because if I do this and I can remove it or I can cancel it out, it tells us a removable discontinuity, which tells us it's a hole in the graph, which then I can then evaluate the limit. If it's not removable, then it tells us that it's a vertical asymptote. And what do we know that a left-hand and right-hand limit at a vertical asymptote is going to approach? Well, it's going to approach either infinity or negative infinity. So let's rewrite this in terms of linear factors. So we still have the limit as x approaches 1 because we can't evaluate it because it causes a problem. So that would be x minus 1 over x plus 1 times x minus 1, because that's the difference of squares. Now we can see here what's going to happen. We can actually cancel that. So once I cancel that, that allows me to evaluate the limit. So the limit as x approaches 1 of 1 over x plus 1 is just going to equal 1 over 1 plus 1, which is 2. So there is an analytical approach of a limit that actually has a removable discontinuity.